In this demonstration, I'll show you a fluid flow simulation of a thermal mixer using ANSYS AIM. AIM includes a number of predefined templates. Today I'm going to begin by selecting a fluid flow template. The template has a number of options. I'll select Include Thermal Effects, and I'll go ahead and execute the template. The template has now completed. It prompted me to select a geometry file. I created the geometry of the thermal mixer using SpaceClaim, and it includes both the fluid and the solid regions. The mixer includes inlets for the hot and cold fluid, and a series of internal baffles to promote the mixing of the hot and cold fluid. The template has also defined a series of tasks that define my simulation process. I have a task for geometry, mesh, physics, and results. By following the task workflow, AIM will guide me through the entire simulation process. I'll begin by selecting the mesh task. The mesh task is in an attention-required state. I can right-click and use the Fix option to quickly navigate to the model input that requires my attention. Here I need to define surfaces for inflation. Specifying inflation will create layers of prism elements adjacent to the fluid wall boundary. An inflation layer is useful for accurately capturing the boundary layer region of your flow simulation. Once inflation is defined, the default mesh in AIM can be specified by setting the mesh resolution slider. The slider controls the overall mesh density from a low to a high resolution. I'll simply accept the defaults and update the mesh task to generate the mesh. Once the mesh is complete, I can review the mesh density before continuing with the problem setup. You'll notice the effect of specifying inflation. There are 3 layers of prism elements adjacent to all of the fluid walls. Next, I'll move to the physics task to continue with the model setup. First, I'll specify the physics region. In my model, I'm only interested in the fluid region, so I'll select the flow volume and apply fluid flow and thermal physics. Next, I'll define a material assignment for the fluid region. I'll change the default material from air to water, and by clicking on the link for water, I can review the material properties included in the AIM material library. Next, I'll apply the boundary conditions. I'll select the cold water inlet and apply an inlet velocity of 0.1 meters per second and an inlet temperature of 30 degrees Celsius. Next, I'll select the hot water inlet and apply an inlet velocity of 0.5 meters per second and an inlet temperature of 80 degrees Celsius. I'll also specify an outlet condition and apply a static gauge pressure on the outlet of 0 pascals. And finally, I'll specify a fluid wall boundary condition by allowing AIM to automatically select all unspecified surfaces as the fluid wall boundary. Once the boundary conditions are defined, I can review the boundary conditions by turning the display of each boundary condition on or off. And by clicking on the boundary condition symbols, I can edit the boundary condition values. Now I'll go ahead and execute the solution. I'll update the results task, and this will execute the solution and compute the fluid results. As the solution is running, I can review the fluid solution residual monitors. And I can also review the actual residual values. Once the solution is complete, I can review the final residuals and post-process the results. First, I'll review the fluid velocity vectors. Next, I'll review a temperature on fluid streamlines from the hot inlet. This shows how the hot water is dispersed and how it's cooled as it flows through the baffles and mixes with the cold water. Note that when post-processing, AIM takes advantage of both the CPU and the GPU to enable rapid results exploration. I can also review the temperatures on a plane through the model and show a cross-section of the mesh on the display. Notice that the tetrahedral mesh is converted to polyhedra. This conversion helps to improve the solution robustness. Now that the flow solution is complete, I'd like to move from a single value analysis to a design point study. I'll identify the hot water inlet temperature as a parameter, and I'll also identify the average temperature at the outlet as a parameter. Once I have parameters defined, I can move from a single value setup to a parametric study. I'll define additional design points to evaluate the average outlet temperature of the thermal mixer over a range of various inlet temperatures. And with a single mouse click, I can execute the entire solution for all of the design points that I have defined. The design point solution is now complete. Note that the average outlet temperature varies by less than 5 degrees Celsius over the range of inlet temperatures. Thank you for watching this demonstration of ANSYS AIM.